Okay, we will now discuss the 13th lecture on module 1 on the course title Advanced Marine Structures. In the last lecture we discussed about the ultimate load design introduction. We discussed 4 limit states which are specifically applicable to design of marine structures, namely ultimate limit state, fatigue limit state of progressive collapse, and limit state of serviceability. We also understood what is the difference and what are the critical questions which are binding ultimate limit state and limit state of serviceability. Limit state of serviceability is a mandatory condition which must be met for every design principle, whereas ultimate limit state gives you an advantage of finding out the ultimate load carrying capacity of every member or a structure as a whole. Of course, these two are very special cases which talks about the progressive collapse because of the damage already created in the system, and this talks about damage caused or the stress level induced in a system because of cyclic loading or repetitive loading. These are all very commonly applied to marine structures, but in this course we will talk about mainly the ultimate load limit state or ultimate load design principles. Now, as we understood yesterday that ultimate limit state or ultimate load design principle has got lot of uncertainties and variabilities. We will talk about this now. These are the factors which affect the ultimate load design mechanism as a whole. What are those uncertainties and what are the different variables, or how do they vary depending upon the assumptions made in the analysis and design. Now, first let us see what is the immediate consequence of having lot of uncertainties in the design process. The immediate consequence is that instead of the design becoming a deterministic process, you should have a definite answer, a closed form solution. Instead of the design becoming a deterministic process, it will now become a statistical process. That is the catch here. The moment I say statistical process, I can always say that there is a probability of occurrence of load, failure of member, etc. So, there is always now a probability being introduced because I am talking about the statistical process. Now, this is an immediate consequence once we agree that my ultimate load design mechanism has lot of uncertainties and variabilities. Now, interestingly, as an engineer, the question comes to mind is, can I avoid these uncertainties so that I need not have to look into the probable values of failure or safety or occurrence of loads? Let me calculate them accurately, let me have a high degree of accuracy in my design. So, obviously, to have a high degree of accuracy in the design process, I must avoid or I must eliminate the uncertainties. If I am able to eliminate the uncertainties, I can be sure that my design process will become completely deterministic. Now, first look into what are those uncertainties, then let us try to answer, can we eliminate them. So, the uncertainties that are present in the system, which are also otherwise called as factors affecting the ultimate load design. I will say ULD here onwards, I will not say limit state, I will say ultimate load design principle. These are the factors which are actually affecting the ultimate load design principle, which are otherwise called as uncertainties. There are many, there are about 7, we will see one by one. Top in the list is the variability in the material quality with respect to the strength and physical properties. I can give an example, Young's modulus, yield value, etc. So, there is a large amount of variability in the material quality in terms of its strength. So, it means however you employ best quality control of production, you will not get a deterministic value of Young's modulus of the material from the workshop, they will keep on varying. For example, Young's modulus of steel should be 2 10 power 5 Newton per mm square, that is what we must get. But from a different lot of production, from different industries, different grades of steel, different composition of constituents in steel, in manufacturing steel, different methods of fabrication processes, different methods of extrusion processes, cold working, hot working, all these complexities put together, you will never get only a single unique value of 2 10 power 5, never. There is a broad range of values varying from 1.95 to 2.1. So, once I say, then I have got to take a mean. So, I am looking into the statistical content back, I cannot have a deterministic set correct accurate one single value, I cannot have. So, that is the variability in the material quality which is contributing to uncertainty. If we talk about strength of concrete, similarly FCK, that is called characteristic compressive strength of concrete. So, concrete strength also varies depending upon the ingredients, constituents of concrete. Okay. So, that is also not a unique value, it keeps on varying. The second is the variability in the geometric properties of members. For example, the diameter throughout the length of the member may not be uniform, the thickness throughout the length of the section may not be uniform, etc. These are actually errors which come from fabrication. You can also call this as errors from manufacturing. Whatever may be the reason you put it, I will get lot of variability in the geometric properties of the member. Instead of saying diameter, I can also say the cross sectional area. Okay. The third factor which contributes to uncertainty in ULD is uncertainty in the specified loads with respect to the environmental conditions. For example, let us talk about wind load. you say the mean wind speed is about, let us say 35 meter per second at a specific sea state where the platform or the structure is proposed to be designed, but does not remain at 35. There can be lot of unforeseen environmental effects which can accelerate this wind speed much more than 35 also. So, there is high level of uncertainty which does not allow you to predict the environmental loads with a high degree of accuracy, etc. The fourth condition could be idealization of a real structure to mathematical model. When you prepare a mathematical model which should simulate exactly the real conditions of the structure, you make lot of idealizations which we call as structural assumptions in the analysis. They all will add to uncertainties in your analysis and design process. The fifth one could be errors created due to the numerical methods which are used in the analysis and design. I am not saying that it is only because of the software, but I do have to certainly write here because of the software. I can even write program also, okay. Software, program coding, etc. The sixth one could be, of course, very importantly, the quality of workmanship. The seventh one could be material degradation due to corrosion, because as you understand, the corrosion process does not affect material uniformly along its depth. As we understand, if I talk about a jacket structure, you will know that this area is going to be the splash zone, is an aerated zone, this is middle and deep water zone. The corrosion is going to be maximum in this area, which is about 50 to 75 mils per year. Corrosion rate is very high. Therefore, the members here or the material here in this zone are susceptible or prone to more corrosion compared to that below, okay. So, when you consider this member as an uniform member of the same material, I am not talking about the length of the member may be discontinuous between the joints, but the material has got to be same. You may agree why it is so. If the material is not uniform, you will again create or induce a corrosion which is called as, when you got two different material joined together, you introduce what is called stress corrosion, okay. So, you will again create a corrosion by itself. So, let us have a common material of the same strength and properties. In that case, the degradation will not be uniform because of one example, corrosion, which is very prominent example in marine structures, okay. Now, there are lot of uncertainties and there are lot of degrees of variabilities which contribute to not having the design process as a deterministic process. Therefore, we have to account for all these variabilities. So, now we agree that the variabilities cannot be removed. I cannot exit from a concept of not having variability uncertainties, because none of them, as you see here, could be avoided, okay. They are implicitly developed in the mechanism, so you cannot avoid them. If you cannot avoid them, we should learn how to live with these uncertainties in the design process. You may ask me a question, sir, if these uncertainties were not new, they were all present when the day a design process was told to a structural engineer in the, let us say, early 1900s, then also it is continuing for the past 120 years, people have been designing structures. Why suddenly we are talking about, or we are giving more importance to these uncertainties and introduce a new design concept called ULS? What is the necessity? The answer is very simple. All these uncertainties will become prominent when you are talking about exploiting the string to the maximum value. If you do not want to exploit the string to the maximum value of its member, then all these can be ignored, because if your EST is 2 10 power 5 and you are talking about ultimate load carrying capacity of this material, but you do not want to stress the material beyond the yield value within which the material remains elastic, we do not bother about them. Even we have a poor quality workmanship, we do not have to bother this in the design stage, because my stress level does not exceed a specific value even much below sigma y. Remember that, it is very important. I have, this is my classical stress strain curve of structural steel. If you say this is my yield value, your strength value for which you will design the section was much below this. This was the design value which people used to practice for a long time, which we call elastic design. So, when your zone of material characteristics lie within the comfortable zone where the stress strain remains elastic, all your principle of superposition remains valid, there is no permanent deformation enabled in the material, that is called plastic deformation. You are not looking at all these advanced aspects of material characteristic, you do not want to exploit the material to the maximum strength of its capacity, etc. You do not bother about them. Therefore, people said, okay, let us ignore all these things for the time being. All became structural idealization assumptions in the design process, people accepted. Then later people realized in early 70s and late 80s that we are wasting a majority area of strength of the material which is having a high reserve energy beyond a specific point. Why do we waste this? Can we capture this? Then introduce the limit state design, ultimate load design methodology, where these uncertainties will come a prominent role, will play a prominent role, because now I am trying to stretch the material beyond the limit and taking it here. Okay. So, I am looking for what is the ductility the material has, what is the load reserve the material has. I want to exploit the material to the maximum possible manner, so I have to live with all these uncertainties. Now, the question comes, uncertainties cannot be avoided, cannot be corrected, but how can we live with this in ULD? The ultimate load design accounts for these uncertainties in a very interesting manner. The ultimate load design accounts for these uncertainties. Remember very importantly, the statement is not reversible. What does it mean is, since I am accounting for the uncertainties in this design process, can I allow a poor workmanship? Can I allow an improper fabrication? Answer is no. Please understand, this design methodology is not a green flag given to the manufacturer, given to the fabricator, given to the engineer, given to the quality inspectors to wave off. Okay, let us not have a poor, let us not have a good workmanship, let us use material of any strength. No, that is not so. Then you will agree, how do we impose this condition strictly in the design, because it says bluntly ULD accounts for these uncertainties. There is a limit beyond which it will not be permitted. Is that clear? So, we are not allowing a broad range of variability, but we allow within a certain band. What is that band? That is what we are going to discuss today. Okay. So, it accounts for uncertainties, but how? By means of safety factors. So, I can redefine what is the safety factor in design, okay. Can redefine the safety factor in design process. Is based on the probabilistic methods with a clear understanding of the variabilities oblique uncertainties and their maximum allowable, that is permissible, limits. So, safety factor is essentially derived from the probabilistic method. To derive a safety factor on probabilistic method, you must have a clear understanding of the limits of uncertainties beyond which you should not allow, okay. So, ULD is seen as an advantageous method because it accounts for all these uncertainties which cannot be otherwise avoided. They are implicitly built, inherently present in the system, I cannot get rid of them. So, indirectly they are handled by safety factors. So, now as far as structure is concerned, there are two components here. One is structure is made of some material, the material has variability in strength and geometric characteristics. So, there should be some safety factor associated with the strength. The structure is subjected to environmental loads which has high variety of uncertainties. So, there should be some safety factor associated to loads. So, there are two safety factors independent of each other. The safety factor associated to the strength of the material is not related to the safety factor which will account for variability in the environmental loads. There are two distinct, explicit, unique safety factors which will account for both of them independently. Interestingly, both of them, they are combined together, forms actually the safety of the system. What does it mean? If the strength of the material is more than the load coming on the material or the member or the structure, if the strength of the structure is more than the load coming on the structure, structure is safe. On the contrary, if the load coming on the structure is more than the strength of the structure is unsafe. It means the uncertainties which are covered as factor of safety independently on load and strength combined together will give you the safety of the system, okay. So, they should be combined, though they are independent, though they are not dependent on each other, but still we have got to combine them to define the safety of the system. Is that clear? Because safety of the system is an indirect manner of accounting uncertainty in the design process, okay. So, therefore, the ultimate load design handles this problem. What is this problem? This problem is combining these two load factors, these two factors, one applicable on load, one applicable on strength together to form a safety factor for the entire system. So, that is a problem. So, ULD handles this problem in a semi probabilistic manner. How? For the strength, we have to define what is called characteristic strength. For the load, we are going to define what is called characteristic load. Now, the term characteristic is a very interesting adjective which is associated to strength and load independently, which defines two things. The term characteristic defines two things. One, the limit beyond which we do not accept the variability. I already said there is a limit, okay. So, the characteristic term addresses two things. One is that limit beyond which I will not accept the variabilities. Two, the probabilistic meaning associated with the uncertainty. It gives a probabilistic meaning to the uncertainty. The moment probabilistic, I say it gives a number, okay. It gives a number. Uncertainty is a general term, okay. It is a qualitative statement. This quantifies that uncertainty with a number, okay. So, I can say this actually quantifies the uncertainty. It quantifies. Therefore, structural member should fulfill or should be chosen. If you remember yesterday's definition of the design, I already said you are choosing the member, should be chosen to meet the following requirement. What is that requirement? Characteristic strength by, I should say, factor of uncertainty. I will tell you very clearly why I am not saying this is factor of safety. This is called factor of uncertainty. So far I am not able to establish whether system is safe, because for the system to remain safe I need to maintain a condition. This is factor of uncertainty which is independently applied only to the strength. Similarly, there will be a characteristic load which will also have a factor of uncertainty which is independently applied to the load, but in this case I will multiply this. If the characteristic strength by factor of uncertainty exceeds or equal to the characteristic load multiplied by factor of uncertainty, I will call this as safe. You understand, there is a classical difference between factor of safety and factor of uncertainty. They are not same statements, okay. Why I am not calling this safety? Because as long as this mathematical equality is not established between these two, I will not know whether this is safe or unsafe. So, I cannot say simply all factors accounting for uncertainty will always lead to a safe design. If this condition is satisfied, then I call these factors indirectly as factor of safety. Is that clear? There is a small difference between the statement of factor of safety and factor of uncertainty. That is why I am explicitly writing here as uncertainty. So, one is divided, one is multiplied. Let us take two classical examples and try to understand this statement. Now, there is a case where the load is exceeded, I should write probably, there is a probability of exceedance, a case where the load is exceeded on the marine structure during its lifetime. Let us say I have a case here, there is a probability that the load will exceed or load has exceeded already in a marine structure during its lifetime. Now, the probability of this to happen depends on, can you tell me what would be the factors on which this probability depend on? It depends on two factors. One, the chosen magnitude, for example, you say you very well know the dead load on a structure, for example, is let us say 11 kilonewton per square meter, that is what you already have seen in the last class. But in your design you said that my dead load for which the system designed will be 5 kilonewton per square meter, by mistake, it was a mistake. So, if you have chosen a wrong magnitude, then there is a probability that this will be exceeded. So, chosen magnitude is wrong. 2, lifetime, you possibly thought the structure will remain 100 years, but structure is designed only for 10 years. So, what is that lifetime we are looking for? Because remember, this is a case where the load is likely to be exceeded during its lifetime. So, what is that lifetime we are looking for? It cannot be infinite, it cannot be very large, it cannot be very small as well. Okay. So, these are the two factors which will decide what is the probability of this exceedance on the service life or lifetime of the structure. Let us take another example. Let us say if a structure is designed for a specific environmental load, I should say, to be in very clear, load combination, there is always a probability of exceedance of this load if the structure is exposed to longer lifetime than it is to be. When you extend the lifetime of the structure, for example, you said the structure should remain only for 15 years, but you are allowing the structure to remain there for 25 years, 50 years, you have extended the lifetime of the structure. So, there is always certainly a probability of exceedance of this kind of load on the structure. Okay. So, it is very important that we must understand the factor of uncertainty, be it strength, be it load. Both these examples are talking about the load. So, we are talking about this uncertainty factor will certainly depend on what is that lifetime we are looking at and what is that magnitude we are looking at. Okay. If you are not able to fix this properly, correctly, with a higher level of accuracy, then there is always a probability that your value will get exceeded. So, ultimate load design mechanism as such may look like a wrong process. The process as such is not wrong, it is that which value you are saying is exceeded is wrong. You have chosen a wrong number, you have chosen a wrong lifetime. You said it is 10 years, but you are allowing the structure to remain for 50 years. Okay. So, you are saying it is exceeding, therefore, the factor of uncertainty should be revised because it is not giving safe results. Is that clear? That is why people have generally a feeling that this design process can have difficulties if not practiced intelligently. So, for beginning engineers, for beginners in structural design, to make the design more conservative, people were not recommending ULD for many years. Okay, that is the reason. So, there is nothing wrong in the process, but still the question critically there is, if this process giving me the maximum load carrying capacity beyond which structure cannot sustain, what happens if this is exceeded even by a chance? Is it a catastrophic process? If it is dangerous, then this design process should not been recommended at all in the first place. Okay, that question is still critical, we have got to answer this. Is it clear? We have got to answer this question. Okay. So, now we have understood very clearly between the limit state of serviceability and ultimate limit state, they are different things. Okay. Having said this, let us now consider two components. What are the two components? One is the load, other is the strength. Instead of strength, I will call this as resistance. Okay. So, load I put as S, resistance I call as R. Now, as I just now said, the loads have lot of variability, lot of uncertainties, therefore, I must design or define this in statistical terms, not on a deterministic value. Okay. So, I have to look for a distribution. Let us say, let the load and strength be represented by normal distribution. So, I draw a figure here. Which gives me both the frequency distribution for strength as well as resistance for the values of R and S. So, I am looking for two distributions, one is for the strength, sorry, the load, other is for the resistance. Let us say this is my normal distribution for the load. This is my normal distribution for the resistance. I call this as R1. I look for two distributions on resistance. One is not having any overlap with load at all, other is having an overlap with load. I call this as R2. I have got two distributions for resistance, R1 and R2. One does not have overlap with the load, one has overlap with the load. Let me hatch that area which is having overlap with the load. So, look at any point here in the hatched area, any point here in the hatched area, you will see that the resistance is lower than the load. So, I can say this is my region of failure because resistance is lower than the load. So, I can call this mean value as mean of load and this mean value as mean of resistance. I am not changing the mean of both the resistance curves, remember that the mean remains same, okay. MR. So, I should say the hatched or shaded portion indicates the failure region because load exceeds resistance in this portion, okay. Therefore, probability of failure can be given as an integral of this section, which is f for x f r x f s x dx. If okay, should be small, where f r and f s are independent. Dependent distributions. Having said this, now we are worried about that adjective statement of characteristic. It should quantify the qualitative statement of variability or uncertainty. Okay. So, the moment I say it is expressed in probabilistic manner, should give me a number. Okay. So, MR and MS, that is mean value of the load and mean value of the resistance, will not have any significant meaning unless otherwise the two curves are expressed slightly in a different form. Let us see what is that form we are looking at. I again redraw the curve. This is the load. Let us say this is my R1 curve with MR1, mean of R1, and I have another curve with a different mean. This is MR. So, what I am trying to define here are the following. I want to define a point in these curves, call this point as SP and call this point as RP. I write MR1 here. This is R, not gamma. Let me rewrite it here. This is RP, this point, and I connect these two as Rp is equal to mu times of Sp. So, how do you get this? It means the mean value of the load and the mean value of the resistance, be it MR1 or be it MR2, anything, should be defined in such a manner that Sp and Rp are to be described. Now, what are these Sps and Rps? Sps and Rps are the characteristic definition of the load and strength respectively. Sps and Rps are the characteristic definition of the load and the resistance respectively. What does it mean? I say Sp is selected in such a manner at 95% or 5% of the tail. Rp is selected in such a way that 5% or 95% of the 5% of the head. That is, if this is 100%, this 5% of this. For these two curves, this is 5% of the head. So, what does it mean? Characteristic load is that which is never exceeded with the probability of only 5%. 95% it will not be exceeded. Characteristic resistance or strength is that where the material property 95% will be acceptable, there is a chance that it can vary only by 5%. So, that is the limit what we are talking about. Is that clear? For example, if you want to really qualify any material in terms of its Young's modulus, pick up the material, find the mean. If the mean is beyond 5% variation, reject it, and so on. Is that clear? We will continue this discussion in the next class.